started. Hi, everyone. Thanks for joining us today. This is Jason Key at SB Grid at Harvard Medical School in Boston, Massachusetts. I'd like to introduce today's speaker is Trent Balius from Brian Associates Lab at UCSF. So Trent's going to tell us about DOC, where it is and where it's going. DOC is a molecular docking package for screening molecules and ligands for complementarity. So Trent, go right ahead.
Thank you. So today I'll be talking about DOC. I'll begin my presentation with a brief introduction to docking and to DOC. I'll describe DOC 3.7. I'll provide a list of resources. I'll discuss how DOC 3.7 works. I'll then give a tutorial on how to run it. And then I'll conclude this section with the features that I want to highlight about DOC 3.7. I'll then talk about DOC 6.8. So DOC, there are two branches that are still being developed, DOC 3 and DOC 6. And so they're actually two different code bases. So I'll talk about DOC 6 as well. I'll give a list of resources for DOC 6. I'll talk about how DOC 6 works, specifically the anchor and grow algorithm. And then I'll discuss the scoring functions in DOC 6 and give a few features that I want to highlight. So docking, in the Shoichet lab, we use docking as a lead discovery tool. I hope everybody can see my title. So we use docking as a lead discovery tool where we take a database of small molecules and then we dock each molecule into our target of interest, and we get a rank ordered list where we have the best scoring molecule at the top and the worst at the bottom. And then from this list of molecules, we then purchase molecules to test experimentally. And in the Shoichet lab, we've had a series of successes, especially targeting GPCRs. And so docking can be used as a lead discovery tool, and we can find molecules that bind our targets. So the two main applications, as I see it, for docking is as a lead discovery tool, which I just described, but also as a way to predict how a small molecule binds to a protein and what is the geometry of how that molecule binds to the protein. To do these two tasks, DOC needs to do these applications. DOC needs to perform two tasks. It needs to sample the geometry of how the ligand binds the receptor. So we generate many possibilities, and then we have to score them and have the top scoring pose be the correct pose, and then also rank. When we dock a series of molecules, we need to rank order them so that we can enrich for binders. I also just want to highlight that DOC, we have a trade-off between speed and accuracy. So in order to screen millions of molecules, our docking application has to be fast. And so sometimes we sacrifice accuracy for speed. And I just also want to note that DOC 3.7 is among the fastest docking programs available. So DOC 3 works by, we do a lot of pre-computing. So we pre-compute our ligand, the ligand databases outside of DOC. So we do a conformational expansion outside of DOC. we generate an ensemble of poses, and then we store it in a data structure, a DB2 file. We also pre-compute our receptor. So we define our active site by placing spheres in the site that we're interested in. Then we bound the spheres with a box and pre-compute the energetics of that site onto a grid to make our scoring fast. And then internally to Doc, we orient a rigid segment of the database onto our spheres, and then we score all of those conformations. Our scoring function in Doc 3.7 consists of 3 terms currently: a van der Waals term for shape complementarity, an electrostatic term, which is like the charge complementarity, and then the final term is a ligand desolvation term. However, because of what we know about the binding event, we're neglecting several important terms such as receptor desolvation and ligand internal energy. So there's directions for improving our scoring method. So there are many resources available. We try and document a lot of stuff on the Shoichet Lab wiki. And so I recommend going to this link, and there's some tutorials that are available. Another good resource is the Doc Fans Archive. People have asked about Doc 3.7 on there, and people have replied. I've replied. So you can use the archive as a resource. I also just wanted to talk about the Zinc database, which a lot of this is a Shoichet Lab and Irwin Lab resource where we have prepared vendor catalogs for docking, and it's a great resource for searching for molecules and downloading doc ready files. And I'll actually walk you through using Zinc in the tutorial shortly. The Dude database is also a great resource, and there's a way to generate decoy molecules on the Dude webpage, and I'll talk about that during the tutorial as well. So for the tutorial, I want to go through 2 scenarios. One is just docking a single molecule into one protein. And so to do this, we can use the Zinc webpage to search for the molecule of interest. I'm searching for erlotinib, which is an approved drug, and I'm going to dock it to EGFR, epidermal growth factor receptor. So we can search for erlotinib, and then we can pull up the page. And for erlotinib, we can download it in different formats. For instance, we can download just the kind of the chemical 2D file formats, but we can also download 3D formats. So, and I'm going to want to download the DB2 file format, which is the file format that stores all of the pre-computed ligand conformations. And so we can, if you right-click on the DB2 tab, you can get the link location, and then you can just use wget to download that into the directory. Then to run doc, you need to put all of your DB2 files in a split database index file. You just need each DB2 file should be on a separate line. We also need to download the receptor file. And for that, we actually need to run our automated procedure. We need a receptor.pdb file and a extol lig.pdb file. And so you can use your favorite mechanism for doing that. For instance, you could use Chimera to help you separate the two files. If your protein of interest doesn't have a ligand file, you can just place atoms in your site of interest. One way to do that would be to use Spherogen, which is a program distributed with Doc. So you can also just use a text editor or use grep to separate out these files. And it's important to remove alternative sidechain conformations. So this PDB file had a B conformation of 2 sidechains. So I separate out the receptor and the ligand. I then run Blaster Master, which is a Python script or a Python program that prepares all of the files you need for docking. And it takes in the receptor and ligand files. And then it generates a indoc file and all of the grids. So the ligand desolvation grids, the electrostatic grids, the van der Waals grids. So in the indoc file, this is just a few of the parameters in the indoc file, and you can modify that. For instance, if your docking is taking too long, you can decrease the orienting sampling step by reducing it from 5,000 to 1,000. You can also increase it if you feel like you're not sampling enough. You can, if you don't observe the pose that you're interested in, you can actually write out multiple poses. So you can change these 2 parameters to 100, for example, and you'll write out 100 poses. We also have recently re-implemented a simplex minimizer, and so you can turn on. By default, it's cut off, but I really recommend turning the minimizer on. And this function just minimizes the 6 translational and 6 degrees of freedom, the 3 rotational and 3 translational degrees of freedom of the ligand relative to the receptor. So to run our docking calculations, we need to perform a few steps. The first is to set up the directories. So although we only have one ligand we're docking, I'm just going to walk you through the procedure if you had many molecules. So you can prepare the directories giving it the split index file. Then once you've built all of your directories, then you run the submit command. Now this will submit your docking jobs to a queuing system. So we use the SGE queuing system. And then once all of your docking jobs have finished, then you can collect the data using an extract all, or combine all of your out doc information, all of your scores into the extract all file, and then generate the poses generating a file that contains your top 1,000 poses by running the git pose script. So doc 3 parallelizes the process by creating multiple directories that contain a small number of ligands, and then submitting jobs for each one of those directories. And then once all the calculations are finished, then you process those directories and create a united file that contains the scores for all of the molecules, and then you can get poses for the top scoring molecules. I hope that makes sense, and we'll go through it again for the next scenario. I also just wanted to highlight that doc, you can run doc locally. You can just run the executable. It's located here. So you can just cd into you can go into the directory that you're interested in docking and just run doc locally. To visualize the docking results, I really like using Chimera and the view doc module in Chimera. And so when you open up these pose files in Chimera, it will create a spreadsheet where you can click on it and see the pose that you have selected, and you can reveal different information in the mol2 file. And here what I'm showing is the best scoring pose without minimization, and then the corresponding pose after minimization. And what we can see is that one is that with the minimizer, that pose shifts a little bit, but gets a lower energy, a more favorable energy. However, because I write out 100 poses with the minimizer, it shuffles and goes further down the list. So, and here is the best scoring geometry with the minimizer turned on, and reassuringly, both the preferred molecule without the minimizer and with the minimizer give you a reasonable geometry similar to the crystallographic geometry shown in cyan. The second scenario I wanted to talk about is ligand enrichment. And so here I'll just show you how you can get known ligands from a database such as Chembol, and then generate property match decoys, and then prepare both the ligands and the decoys for docking and docking them. So to calculate enrichments, you need a set of known binders and a set of decoy molecules. And then you can dock those molecules and generate a rank ordered list. And what you want to happen is the ligands bubble up to the top of your list. And so in blue, I'm showing a good enrichment, and in red is a poor enrichment. And I'm showing the receiver operator characteristic curve. And one way to quantify enrichment is to calculate the area under this curve. And you can see that if it is above the random line, it is good enrichment, while if it's below the random line, it's poor enrichment. I hope that makes sense. So how can you perform these calculations? Well, you can go to Chembol, which is a great resource, and you can obtain molecules that have been curated from the literature and for your target of interest. So I searched for erlotinib and downloaded the molecules with Ki values. And I then downloaded the spreadsheet, and then I took the top 12 molecules at the top of the spreadsheet and generated decoy molecules for them using the dude web server. And then I I submitted for the web server, you can paste your smiles here and then generate decoys, and then they'll email you a link to download your decoy molecules. And then you can just unzip the file and process the results into a single smile file. We provide scripts for building databases. However, one thing to keep in mind is this ligand generation pipeline has a lot of requirements. You need to have several programs in order to generate these molecules, and it can be a little hard to get working. So you can also download the molecules already prepared from zinc if you know which molecules you want, or you can actually get databases from the dude webpage. We have 100 a little over 100 dude systems in our dude database with the ligands and decoys already prepared. But I wanted to, if people were interested in how to generate the DB2 files, this is how you do it. And I also have a wrapper script that will break up your smile file into chunks and then submit each chunk to the queue, so you can parallelize the ligand building preparation. And this script you can find on our wiki, and I provided the link here. So also, to run our enrichment calculations, we need to create the split database index files again. And we also need name files, the list of names for the ligands and for the decoys. And then to actually run our docking, we can again run the setup script where we prepare our directories. Each directory contains a number of molecules. And then once the directories are prepared, we just submit the jobs to the queue, and then we wait for them to finish. And once they wait, we collect the data and get the poses. And then we can also run, we provide an enrichment script, and you can give that script the list of ligands and the list of decoys, and it will calculate the enrichment for you, and also make enrichment plots. And so I did this twice with and without minimization, and we can see that with minimization gives us better enrichment, 3 log AUC units, well, more than 2 log AUC units better with minimization. Okay, so the two applications I think I have described are really sanity checks for to be used before you perform a screen. And so once you're happy with the setup, your receptor preparation, then for ligand discovery, you would want to perform a virtual screen. And so you can use zinc to download molecules for your screen. And so I like this feature, the tranches features on the zinc webpage, where you can see all of the molecules in this histogram, all of the molecules divided up by molecular weight and so size and hydrophobicity, so the log p values. And you can see that in zinc, the 2D representation, there are 375 million compounds represented in zinc. And then you can select different options. So for instance, you can select the molecules that have 3D properties. Purchasability, we want to just dock the molecules that are in stock. And then, and we also just selected the lead-like molecules, so which is this subset of the zinc, of this log P and molecular weight part of the database. And then once you're have selected the molecules that you want to dock, then you can download them. So like you can download the URL, a raw URL file that contains the links to all of these databases, and then easily download them onto your system, your computer system, and then dock them in a similar way as I described with the enrichment calculation. So to conclude the Doc 3.7 section, I just wanted to mention some of the some additional features or features I want to highlight. So Doc 3.7 also has a covalent docking method implemented. So you can actually screen for molecules that form covalent bonds with your receptor. Work that I've been involved in is improving the dock scoring function by incorporating in a receptor desolvation term. We have reintroduced the minimizer into the code, and it seems to help most of the time. I also just wanted to re-emphasize that Doc 3.7 is among the fastest docking softwares. And the other thing I wanted to mention is chemical space continues to grow. So the purchasable chemical space continues to get bigger and bigger. And something that we want to do in the Shoichet lab is to be able to dock all of the molecules we can buy. So so we want to be able to dock 100 million molecules and more as chemical space continues to get bigger and bigger. So so I just wanted to mention that. Okay, so for Doc 6, there are a lot of online resources available. There's the Doc 6 manual. I really recommend the tutorials from the Rizzo lab. I think they make Doc very accessible. the doc fans mailing list has a lot of information about how to run Doc 6. And for both Doc 3 and Doc 6, if users are having problems, I really recommend emailing the mailing list. Often people will reply pretty quickly. So Doc 6 is different than Doc 3 in that it samples ligand degrees of freedom internally to the docking internally in the doc program. So instead of doing it outside, instead of pre-computing the ligand conformations, it does it on the fly. And it does it by first breaking the molecule up along the rotatable bonds, identifying a anchor, a rigid segment, the biggest and rigid segment with the most connection points, and then going out in layers until the molecule is fully grown. And because this is done internally in doc, we can prune away unreasonable conformations of the different segments, so we can actually prune our growth tree as we go along. So just similarly to Doc 3, in Doc 6, we also place spheres in our active site, pre-compute the energetics on grids, and then orient the molecules to our spheres, and then score our molecules on our grid. But the difference between the two is the anchor and grow algorithm. So Doc is internally sampling the degrees of freedom of the molecule, and the scoring function is actually guiding the growth to some extent through minimization at each stage of growth and pruning, trimming the growth tree down. And I also wanted to mention, as a difference, Doc 6 is parallelized through MPI and does a lot of the bookkeeping that we do through in Doc 3 through processing scripts. Doc 6 takes care of it internally through the MPI implementation. Another really nice thing with Doc 6 is there's many scoring functions available for users. The scoring function I think that's used most for the docking is the grid score function, which has two components: the van der Waals and electrostatic component. However, there are several other functions that are available, and there are also several rescoring methods available for users. The features of Doc 6 is there are an array of nice scoring functions. New to Doc 6.8 are the descriptor score scoring function and the pharmacophore scoring function. Something that's going to be coming out soon is de novo design in Doc 6, which will take advantage of the anchor and grow algorithm, but modify. It will grab different anchors and side chains from different molecules and create new molecules. Another great thing about Doc 6 is it's a very modular program, so it's easy to implement new scoring functions or new sampling methods. And it's also parallelized using MPI, the message passing interface. And with that, I would be happy to answer questions. So that concludes my webinar.
Great, thanks, Trent. If anyone has questions, you can send those to me by chat. Just send them and I can pass them along. I had a few during the course of the talk that I think you answered along the way. So if those weren't answered, feel free to send me a chat. I can pass them on. I had a couple of questions. Um, one that I had sort of touches on this idea of the de novo algorithm from Doc 6. Is it currently possible during the growth phase to extract like fragments or sort of subconformers of the molecules? You could imagine a scenario where you've got a molecule, you've got a great fit, you've got a really great score, and then you add that terminal methyl and like, okay, clash. It doesn't, your score goes through the floor. But the compound you had before was good, right? So, but you don't necessarily know that on the fly. Are those identifiable?
In the de novo design method, yes.
Okay. But
So go on.
oh, I was just going to say, but not currently.
Um,
Those scores are internal during the growth process to they're not.
we typically don't write out
I mean,
uh, intermediate confirmations. I think there's actually a flag where you can ask Doc to do that, but
okay.
I don't think I've used that flag. But the thing about these intermediate confirmations, they're a bit uh, artificial because the charges are actually for the fully grown molecule, and often the if you don't have the fully grown molecule, the you might be missing, like if you capped it, you would also need to add like a hydrogen, or it might modify the chemical
So
structure of the
your
molecule.
partial charges are all based on your full molecule, what you're intending to build, and not necessarily
Yeah.
have. Yeah, yeah, I can see that.
So so I think that's one of the issues with anchor and grow is the intermediate molecules that you're actually optimizing your growth on are actually um, a little fictitious because they're constructed with um, based on the full molecule. So
Yeah.
um,
Another question that I had, just a simple one, but 3.7 is Fortran. Is that and you mentioned that it's faster. Do you have a compiler recommendation? I mean, this is mostly for me, but
yes,
are Intel compilers faster?
we use the Portland group compilers.
Okay.
And we actually distribute an executable when you download it. So it's actually pre-compiled for Linux for you. And I think usually it works pretty well for people. But yeah, when we compile it, we use the Portland compilers. Um,
I, one question I had from a listener was comparisons of speed. Could you give us, I don't know, sort of ballparks? The question here said, how does Doc compare to Rosetta in performance? Maybe you could just compare 3.7 and 6.8, or maybe relative comparisons to other tools that you might be familiar with.
so Doc 3 is probably like 2 orders of magnitude faster than Doc 6. So it's much faster than Doc 6. Um, we per molecule we spend well under a minute per molecule. It's we're spending seconds per molecule, and some of this is adjustable by the parameters in the indoc file. Um, but and I really need to do a more robust evaluation of how much time we're spending per molecule. I, it was that is that sufficient or do
Yeah,
you?
no, I think that's good. I mean, another question, and this is something that a user passed in and I've wrestled with too, is that when you have packages that have 25 scoring functions built in, it's not always obvious which way to go. I mean, is there a consensus on either scoring functions that would be best way to start, obviously better than the others, or a workflow for predetermining or determining the best scoring function for a project?
So I would really recommend doing some of these retrospective studies to evaluate the scoring functions. For Doc 6, I think what the Rizzo Lab mostly does is they use the grid score for the initial docking, and then they'll use um, like footprint score for rescoring or descriptor score for rescoring, where they can um, take advantage of perform more expensive calculations on the best scoring molecules. In Doc 6, I mean, in Doc 3, we only really have one scoring function, but we can turn on or off different components. So in Doc 3, we only have we now have four components: the ligand, the van der Waals, the electrostatics, the ligand desolvation, and now a receptor desolvation. We also have a way to provide a receptor um, energy when you're docking to multiple conformations of your receptor. And we also have a way of turning on ligand internal energy, although that's not been very well validated. So for Doc 3, it's more, do you want to turn on these different components to this one scoring function? Did that so and in terms of evaluating it or testing it, the retrospective analyses can give you some sanity checks to make sure you're on the right track. So
Yeah, I can imagine that you could do something like the for the dude, the systems that you mentioned on the dude database. You said you had about 100. You could probably run through a selection of scoring functions for each one of those, and then look at decoys versus known binders, and try to make some sort of assessment. But
exactly.
yeah, but that would be, a PhD and a half worth of work, I think.
Yeah. Well, I think what we often do is we'll focus on the system that we're docking to, that we want to perform the screen on. So, and then you can tweak the setup in different ways. So, before we ever run a screen, we'll do an enrichment calculation, and if the enrichment isn't sufficient, then we're not satisfied with it, we will tweak our setup. So we'll adjust the spheres that we're docking to, or we'll change we call it, we'll make certain residues more polar by adjusting the partial charges, or we do some tricks to bring up our enrichment before we actually submit our screens. So
All right.
does that make any sense? Does
Yeah,
that make
yeah,
sense?
that's great. So with that, I think we can wrap it up. Trent, thank you very much. Very informative. Glad to see Doc coming along. SB Grid users 3.7 and 6.8 are currently available in the tree. Give them a try. If you have any issues, problems, questions, send them my way. And as always, you can also check out the Doc Fans mailing list. Seems like a great resource, place to get started. So thank you very much. And everybody,
Thank
take care.
thank you. Bye bye.
Bye.